if you have two binomials, and in the first pair and the second pair, the objects are the same, only they're separated by a different sign, the result is going to be whatever is in the first position, doesn't matter which one you point to, squared, minus whatever is in the second position, squared. This is known as the difference of squares. Two squares to be exact. This type of product is known as the difference of two squares. Now, I gave you a real easy example, x plus 1, x minus 1, and lo and behold, the answer is a squared, which is the first position, minus b squared, which is the second position. I gave you one slightly more advanced. Lo and behold, the result is a squared minus b squared. So this pattern, to repeat, will always create a product that can be described this way. A, just marking the first position. B, just marking the second position. Let's do just a couple more that can kind of help us visualize what it is we're looking at. Example 2 in your textbook, I'm going to do my own, but example 2, slightly more difficult. Not too much, I would say. Here's example 2. It just requires a little more work. 3y squared minus 2z multiplied by 3y squared plus 2z. Okay? My question to you, again, I'm trying to get you to memorize patterns. Does this binomial appear to fit this pattern? If so, rather than foiling it, you can simply state that the product then is the result of squaring the first position. What is the result of squaring 3y squared? 9y4, right? Minus, what is the result of squaring the second position? 2 times 2, 4z. Yep. Okay? Because we've learned that this layout in a multiplication problem produces that result, we can translate it when we are told to multiply binomials and say, I ain't going to FOIL this. I know that this and this are the same as this and this, only separated by a positive and a negative. Identifying it as a difference of squares type of a problem. So if I have this, I create that. 3xy plus 4z, 3xy minus 4z. Is that one of these? Same thing in the first position? Yes. Opposite signs, plus minus, doesn't matter which one's first? Yes. Same thing in the last position? Yes. Therefore, I don't have to FOIL it. I can square A. A is 3xy. What's 3xy squared, guys? Anybody know what 3xy squared is? Yep. Minus, because I know that that's what's being produced. B squared. What is B squared? 4 squared. Z. Yep. Awesome. So what these two examples have attempted to teach you is to recognize a pattern and use a shortcut, which is your knowledge, to attempt to quickly multiply something and get your answer without actually having to go through the whole FOILing process. Okay? The last couple things I want to share with you for the rest of this lesson is going to be, what if I tell you to factor something? In other words, give me the items that when multiplied together would create it. That's what I'm going to move on to here. Oh, look at me, I wrote example squared. Example 2. That's funny. Example 3. I'm going to rewrite that pattern at the top of the page. A minus B times A plus B will always produce A squared minus B squared, aka difference of squares. All right, here's example 3. What if I say to you, factor A squared minus 49. Factor. If I give you this and I tell you to factor it, I am asking you what items, when multiplied together, will give me this. Does this sort of look like this? Yeah, this is a difference. Is the first piece a perfect square? In other words, does it have a square root? Does the second piece also have a square root? Yes. If you can look at a piece and identify that is a difference of two items with square roots, if you can look at a binomial and say that it is this, then it can easily be factored as follows. The square root of A squared is what? Place that in the first position. Place opposite signs as your operators in each one. What's the square root of that? You have just factored, my friends. You're done. Factor this. Again, I'm making it easy because all I'm giving you is this, and that's really all you're going to see in this lesson. Later in life, you'll have to disseminate between different things. But so, is this the difference of two things? Is this a binomial?
Yeah.
So it's a difference. Are these two items perfect squares?
Yes.
Then you can factor it as follows. The square root of the first piece goes in the first position. 6 and 6. Opposite signs. It doesn't matter, plus, minus, or minus, plus, as long as it's different. Square root of the second piece, what's that? Goes in the second position. Ta-da. I know. Not hard at all. Let's do another one. Actually, let's do 6 and 4. Remember, an item with an even number, an exponent with an even number, cut in half is its root. Anyway, is this a difference? Yes. Is 25 a perfect square? Is 64 a perfect square? It sure is. 8. Q to the 6 is a perfect square. Its root is q cubed. Q squared. Q to the 4 is a perfect square. Its root is q squared. Which means it can follow the pattern. What is the square root then of 25q6? 5q cubed. When you are doing an exponent, if it's even, cutting it in half gives you its root. That goes in the first position. separated by opposite signs.